So, last time we were talking about capillary behavior. And so what we'll do is move on from there. So our usual deal is, if I get this get it working, is to give some kind of recap. And so we're talking really about capillary tubes and interfacial tension on surfaces and around grains, and so we'll perhaps recap on that. But then what we'd like to do today is perhaps put in the context to deal more with real porous media, bead packs. And so we'll work our way through here, and I think what we'll do today is, once we've recapped, we'll talk about how you get these things experimentally. Went off the bottom. And then work our way back up from here to here. So that's our plan. So, recap is this. This is the big picture, I guess. And so we talked about all these different situations where if you have a spill, we'll get this chimney or column of smear as it goes down to the subsurface. This is obviously a NAPL because it's gone across the water table, denser than water. And at some level it's pooled in a lens because it can't go any further. And we now know that the reason it can't go any further is because it's a capillary barrier. And so that was our reason for talking about capillary behavior and interfacial tension last time. The architecture of these, I guess, could be different based on different amounts being spilled. This, I suppose, would be something that had lots of layers in it that were small capillary barriers, so it ponds and then it rolls off the side and it goes down to the next one, pools and then goes off the side. So this would have some structure in it. But most importantly, we want to really understand what the mechanisms are by which this capillary barrier works. And so we didn't cover this particular part, but we certainly talked about individual capillary tubes, and we could characterize the height rise that you'd get in each of these tubes according to some relatively straightforward equation. We calculated it by just cutting this off here and calculating the force we had to apply to hold up this column of fluid of some weight. And if we balanced all the forces, we got a height rise, H sub C, capillary height rise, which is proportional to the interfacial tension and inversely proportional to the diameter. So as this gets larger or this gets smaller, the height rises. We typically were kind of thinking that this might be water and air above it, but it doesn't have to be. It could be two different liquids, not necessarily a liquid and a gas. It could be two different liquids. And if we define this term called capillary pressure as the pressure in the non-wetting fluid, which would be in a water-air system, the non-wetting fluid would be air, nitrogen, essentially, and the wetting fluid would be water. And so the difference between these two pressures is called capillary pressure, just by definition. And we could define that as the unit weight of the fluid multiplied by H sub C, which would give us that. It's somewhat, we also made the case that the important thing here is that there are different pressures on either side of this meniscus, because this is a catenary, which is a cosine H curve, which is holding up this fluid. And so it has to have tension attached to where it attaches onto the glass. And so this is in tension. So the pressure is atmospheric in the air above it, but less than atmospheric in the fluid below it, because it's pulling, just like hanging a clothes, a weight on a line. The line is going to be in tension. And so this is typically a negative pressure. Negative minus a negative gives us a positive capillary pressure, which is the difference between them. And so our interest in doing that was in being able to think of a porous medium as either a bundle of capillaries, which are of different diameters, or a bunch of, hey Sean, a bunch of grains in contact, which would have a donut at the contact area, which has two curvatures in it. So they're different representations of a porous medium, but they have the same kind of characteristic behaviors. We showed that, either in terms of the height rise or the capillary pressure. And we are interested in being able to define these amounts because we'd like to be able to define our porous medium in terms of how much is solid. There's a void space, and the void space can be occupied by two individual component fluids, a non-wetting and a wetting fluid. And it matters something about the architecture of the capillaries, in that if the capillaries were all in parallel to each other, then the fluid would get hung up in the narrow ones but not in the big ones. And if instead the porous medium was of a structure that was a wide capillary and then a narrow capillary in series, then it would get hung up on this small bridge here. And so the behavior in these two systems would be important to discover because the outcomes are completely different. This would capture, nothing would get through this, but this would allow stuff through in the big one. So we need to make the jump from capillary models into real porous media. Before we do that, maybe it's worthwhile talking about this particular case here, and that is if we think that if you get large open pores, and I guess actually before we do that, let's do this. So let's do this. I should get rid of this. Let's see if I can do that. I guess it's written on there, but we don't need it. Great. So if we have this system here, what green might work. So obviously here are beads, individual beads, and pore throats between them, and pores in the space between maybe groups of 3 or 4 beads. So the largest spaces would be the pores in the middle, and the smaller constricting spaces would be the pore throats. And so we now understand a bit as to why this behavior might be. So if we looked here and we drew, actually if we drew a small square here, we might find that the saturation of this would be about 100% of whatever the red fluid is. Red is the non-wetting fluid. Water is the clear fluid. And so in this pore throat, it might be 100% saturated with water. But if we draw a bigger REV, we talked about representative elemental volumes last time, then that probably isn't the case. The saturation of the non-wetting fluid, I don't know, might be 80%. And the saturation of the wetting fluid might be 20%. I don't know what whether those numbers are right or not. But even though it looks all red here, there'd be some mixture of these. And we know from what we talked about last time that the distribution of these two fluids would be in different locations as well. They'd be present with the water surrounding the grains. And as you put more and more water in, then you end up getting a bubble of the red fluid stuck in the middle. And so that will change as it behaves. But we also now understand a little bit, perhaps, about why these ganglions might go down here. So you'd expect that in the transit of this, that these fluids are looking for the largest diameter pores that they can, or pore throats that they can go through. And presumably they're finding a larger diameter pore throat here than they are here because they're not going through this. And so immediately our understanding of the distribution of pore throats says something about why we might get these little stringers that come through here. And so the other thing that we might like to do is that instead of looking at these individual, you could think of this, I suppose, as a dominant, you can't see the green very well on the blue background. And I guess you can see another thing here, is that if you look at the grain size here and the grain size here, they're different. And so you see that the rough boundary between these is along this grain size boundary here. And it's really easily invaded this because the pore throats are large, but it's having a hard time getting through this and only choosing some choice locations, perhaps where it ekes out the biggest potential capillaries that it can go through. And so we'd like to be able to describe in some way the distribution of the saturations within this porous block. And so that's what we'll talk about today for equivalent porous media. But before we go there, let's go back to this. So the one thing we didn't talk about last time is that was our last slide. So if we think that the largest, most open pores are going to be the ones which will allow this stuff to pass most easily, then we think that big features like fractures, which are quite open, if you look at on the bypass on 322, go through some little limestone cuts, you can see fractures in those. You could do the same kind of analysis we did for the capillary behavior within a fracture. So take two glass plates separated from each other by some small aperture, make that aperture small, and then see what the fluid rise is up between those. You do exactly the same as you did before. You take the weight of the fluid, which would be a volume. This would be the volume. So the distance into the page, the width, and the height. So in other words, this zone here. Would be this. And multiplied by the unit weight, that gives you the weight that's pulling down here. So this whole term, uppercase W, I guess, would be, yes, this includes gravity, right? So this is the mass times gravity. And pulling it up, there's two sides of this. It's of length W. The interfacial tension is applied along this dotted line here. And so if you equate these two things, you get a height rise which is proportional to the interfacial tension, inversely proportional to aperture now. It's got a different coefficient, 2 instead of 4, but it's essentially the same equation. And if we wanted to multiply this by unit weight and unit weight of the fluid, water in this case, then you lose both of these, right? These both go to 1. And so that's this expression here. So again, it's really saying that the difference between the pressure in the air above this point and the pressure in the fluid below it is a differential pressure, PC 0, we'll call it, and it's equal to this term here. And so that's fine. So now we've got an expression that we looked at, which is for these two parallel plates and also for a capillary. But that only represents a single pore in the system. And what we'd like to do is be able to incorporate those all together in some way. And so we can use our understanding, if you like, of those two behaviors to maybe look at real rocks and use those to determine what we'll call capillary pressure, which we know is now by definition, and we know what saturation is. Saturation is the amount of the fluid within the pore space. 100% water saturated, no air in the pores. 50% water saturated and 50% non-wetting fluid saturated, then that's the distribution of those. So let's look at that. So instead of talking about the stuff in this, let's go to 2.3 and then work backwards. I think it's easier to do it that way. So this is the idea here. So imagine not a thought experiment, an actual experiment. So what could we do? We want to know what the distribution of saturation would be in that bead pack that we just looked at. And so if we wanted to measure that and quantify it, what we could do is we could take a core, a cylindrical core, and we could put that core within this sample, in which case we have a pressurized fluid. So this would be a non-wetting fluid, and this would be a wetting fluid. And we have some kind of frit on here, with a pore space which is enough to keep this non-wetting fluid from getting across it into the water. And we surround it with this non-wetting fluid, say a solvent or whatever it is, oil, could be gasoline or could be oil. And we pressurize this. So this will start off 100% water saturated because it's only got brine in it. It's contacting across this frit directly with the brine. And so what we could do is we could do this. And this is pressure in the non-wetting fluid. And this is saturation. And let's call it the saturation of the wetting fluid. And the saturation of the wetting fluid can go from nothing to something. The maximum value can be 1. And this could be 0 pressure, and this could be a large pressure. So the core starts off with only water in it. If we increase the nitrogen pressure that's driving this other fluid, the liquid, the non-wetting liquid, then it starts off at this point here. We increase the pressure to this. If the largest pore that's present in here is too small for the other fluid to go into it, nothing will go into it. So if you increase the pressure some more, maybe at this fluid, some of this blue, let's call this blue fluid, will invade it. And if it invades it, the only place for the water to go is into the brine below it. So if it invades it at the expense of the water, then the saturation of water will go down, and the saturation of the non-wetting fluid, which I guess would be on the top here, saturation of the non-wetting, they'll be the reciprocal of each other. This will be 1, and this will be 0, right? There's no non-wetting fluid in this. So as you get above the point at which it invades, then the pressure here will stay constant, and you'll end up with a proportion lowering of the water saturation at the expense of adding non-wetting fluid. Then you increase the fluid pressure again. Same thing happens. Initially nothing goes in, but now it'll find the next smallest pore that it can invade, and so some more will go in here on the next smallest pore. So the saturation will change again, go to some number. You keep on doing this. Each time it will be keeping on invading a smaller pore space. And this transit point here is just irrelevant. We're interested in the steady state behavior. So it's steady state saturation here. After it's reached equilibrium, steady state here, steady state here. And so if we join those points together, I won't be able to do it very well. It'll look something like this. So if we keep on going up with this, those will be the points we get each time. And then at some stage, what will happen is if we keep on increasing the fluid pressure, nothing will happen. I don't want to do that vertically there, but it will go over, but ultimately will go vertically. There'll be no change in saturation. So now what we could do is you could drop this pressure off. If you drop this pressure off, then you're going to start from some location here, I guess. So this is our last location. I wanted it to be blue. So now what's going to happen? You're going to drop the fluid pressure. It's going to go down to somewhere. It's going to now suck this water back in. It's because it's water wetting. It means the quartz is hydrophilic. It loves water. And so it wants to get the water in at the expense of the non-wetting fluid. And so it will now start to expel the non-wetting fluid. So this, if we go in this direction, at this point, drop the pressure again. This is the equilibrium point. Drop the pressure again. Maybe this is the equilibrium point. And so these are the equilibrium values, right? Each time you've dropped the pressure, it's out of balance. It's allowing more of the non-wetting fluid to come in. Once it's here, everything's in balance. All the forces are in balance. And so the other curve that you can draw on this, I think this is your assignment number 3, by the way. Joining these will look like this. And so this is the capillary pressure versus saturation curve. PC versus saturation curves for a real porous medium. It's relied on the fact that these tubes or capillaries are being invaded, and these little ganglions are developing, just like we looked in the picture with the red fluid invading the water beadpack, water-saturated beadpack. And this curve will be a characteristic of a porous medium. And so in this, what we'd like to know is this magnitude here will be the minimum pressure at which we can invade. So until we get to this capillary pressure, there'll be only water in the system. And so we'd like to perhaps know what this is, and we'll call this the capillary pressure 0, at 0 saturation. And as we keep on increasing the pressure, then this will follow this. I guess the important thing to note is also that it's hysteretic, right? It goes, it drains water along this curve, but it imbibes water along this. And so this will be called, as we'll find out, I've got no space here, this is the drainage curve. And this is the imbibition curve. So, and you have some, well, don't worry about this. So what you could do, obviously, as you put more water into this as it comes out of the core, the height in this, if it's a very thin capillary here, this will register the volume change. So you can calculate the volume change of water in here. And if you know the volume change, you can calculate what the change in saturation would be, right? We know that saturation is equal to the volume of water divided by the total volume. And so if we know what the change in the volume of water is, and we know what the, it's not right, is it? That's the volume of voids. So if we know the volume of voids in here, which we could quite easily do by taking the density of the quartz and knowing the volume of the core. If we know how much the volume of water changes in this as it rises up here, then we immediately can calculate the saturation. If we can calculate the saturation for each pressure change that we apply, we could calculate what the jog is over here, because we're measuring this volume of water. This is got by measuring the volume of water in the system. And of course, we do this through score for the volumes. So that's our way of being able to get a handle on not what the capillary behavior is in terms of single capillaries or single grains on grains or single fractures. Those tell us what the mechanisms are by which this occurs, but they don't give us the picture of what this would be for a real porous medium. And so this would be how we'd get the experimental results for that. Right? So-called capillary pressure versus saturation curves. Yeah.
So when you drop the pressure again and the water reinvades, will the water, because I noticed on the bottom point when the pressure back down to 0, the water doesn't reach full saturation as you drew it. Is it never going to fully be able to push out?
No, because this is the smeared chimney that you have. There's some of the red fluid left in the pore space, and the water can't push it out because it's held by capillary forces. Yeah. So I purposely did it so it doesn't. So this is, so the other features that, I can't draw those figures very well. So, well, let's see it on the figure that we have here, because they have very specific terminology. So.
That's kind of like the case of when we talked about before, if you have, when you pump a bunch of water into something and it kind of surrounds that non-wetting fluid and
Yeah.
like a blob, right? It's kind of that
From from the pictures we had here. This, yeah, that's exactly what's going on. And so in each of these cases, you're even at the final stage, you're not 100% water saturated because you've got a bubble of oil in here. Or in the case where it's non-wetting, you've got a bubble of water in the middle and oil surrounding it. And so that's what we're trying to represent. And so the characteristics of this are shown here. And we can label these terms. It's perhaps worthwhile doing this. Again, you see here, the saturation of the non-wetting fluid goes from 0 to 1. The saturation of the wetting fluid goes from 0 to 1, but in the opposite directions. And we can label some components. This component here, well, this is a bit more complicated because it's on a, yeah, let's do it. I'm going to draw it here, unequivocally. So I'm going to draw the same diagram we had before and just label each of the terms. See if I can draw it better. No, wrong. Saturation of water, 0, 100%. Saturation of non-wetting, 0, 100%. Capillary pressure equals pressure of the non-wetting minus the pressure of the wetting. This we'll call PC0 equals the entry pressure. In other words, the pressure you need to apply to get the first bead of this non-wetting fluid into the system, because it starts off at 0 saturation. This we will call as this we will call SW0, and this we'll call SNW. SW0 equals the irreducible saturation of water. Of actually wetting fluid. And SNW0 is the irreducible saturation of the non-wetting fluid. And those kind of define the ordinates of our figure. This is the drainage curve. As water drains out of the system. And this is the imbibition curve. as water is re-imbibed, sucked in, because it's attracted to the quartz. So it automatically gets sucked in by just like capillary rise in a towel or a filter paper put into water. Exactly the same process. Okay? So those are the important features. So what this says is that if you start off with a water saturated sample and you force this other fluid into it, you'll reach a limit that you can't get any more of that fluid into it. Or you can also think of it that you can't reduce the water saturation by more than this amount. This is, so in any point here, I guess on any of these curves, it's going to get a bit busy. I suppose this would be, this amount here would be the saturation of water. And this amount here would be the saturation of the non-wetting fluid. Every point on this curve would be split. Has to together equal 100% because it has to completely fill the void space. So what isn't filled by water has to be filled by the second fluid, which may be a liquid or maybe air, as we'll see later. So this is actually, if you understand this figure and can define those particular points on it, then you have pretty much all you need for the first 3 weeks of this class. So that's an important figure, okay? So that's what a real porous medium would look like. So we've moved from saying that we understand how things will be sucked into fractures and into capillaries as individual bundles of capillaries. So the way you could think of a porous medium would be as a whole bundle of these individual capillaries of different diameters. And so that might be a good model for us to use. But we don't actually have to do that. What we can do is we can take a real porous medium and put it in the apparatus we just talked about and force another fluid into it and measure the pressure we have to apply. So in other words, we'd have all of these individual points on this curve by just incrementing the pressure each time and measuring the amount of water that was forced out, and then measuring the amount of water that was allowed back in as we go back on the other side. That's it. So we could get that curve in theory for any material that we wanted to just by doing that simple experiment, physical experiment. But what we might like to do is, it's actually not a very easy experiment to run, and so it might be helpful if we could characterize the behavior in some other way. And so what you could use is you could use Buckingham pi, if you can remember back to that. And you can do a dimensional analysis to get the minimum number of parameters that might describe a system. And you could describe this system by linking this behavior of this curve, which we've just drawn, right? This curve here is this. But instead of being capillary pressure, I didn't put that here. This is capillary pressure. I guess I did, sorry. Then you could draw a similar curve, but you can parameterize it in a different way. Still with the saturations, so 0 to 100% water saturation and 0 to 100% non-wetting saturation. But the capillary pressure you can represent by another expression. So this is the capillary pressure. This is the interfacial tension that we talked about before, but this is the measured permeability of the system and the porosity of the system. So you have those defined here. And it turns out that if you do this analysis, it turns out, and we'll show it later, is that this P0, this is what we called PC0. So it's the pressure you have to apply to get an infinitesimal amount of the non-wetting fluid to invade this core. It happens at a value of 0.3. We'll show why that is later in the class, but we won't do it today. And so this curve is a very difficult curve to measure. But if you can parameterize it in terms of these parameters, this is an important feature for us to know, and we'd like to be able to measure this. If we know that this value at the first invasion is equal to 0.3, then we know this. We can easily get the magnitude of the interfacial tension. It's just a property of fluids. We can often measure the permeability in the field of an aquifer, and it's pretty easy to get a porosity. Porosity might be between 10 and 30%, and so we can get that. So the point here is that if we know this expression here, and we know what this ordinate is, we can get this PC0 just by knowing everything in this equation except for PC. And so we would typically do that. And so this ends up being useful. So this ends up being kind of a universal curve, which is true for all porous media, and we can use it. And we can always recreate this curve if we can link it to the permeability, which is a much easier parameter to measure in the field by pumping tests. You talk about Theiss tests in 452, steady state pumping tests, transient pumping tests, measuring permeability in the laboratory. Been too long? A year ago? A year and a half, right? You've taken it. But for some of you, not, right? Well, anyway, so you can get permeability. And so that this is an important curve, so-called Leverett curve, after its originator. Older even than me. Can you believe that? So that's one useful parameterization using non-dimensional parameters. And of course, this J parameter has no dimensions. Capillary pressure is in newtons per meter squared. Interfacial tension is newtons per meter, because it's a force along a circumference of the rim around the capillary. Permeability is in meters squared. Porosity is dimensionless. So square root of meters squared would be meters. So newtons per meter squared times meters over newtons per meter turns out to be no dimensions. No dimensions at all. So this is a useful expression, and most importantly, this ordinate here is useful, because if we get this, we know what the invasion pressure we have to apply to invade it, and we can surmise that this pressure might in some way might be related to this height, right? If you have a column of this red fluid sitting within here, you know all about buoyancy. The reason buoyancy works is that you have a balloon, the pressure acting on the bottom side of it and the pressure acting on the top side of it are different because this is deeper. If the balloon is water filled in the tank, then this extra water in the balloon exactly balances the top pressure plus the weight of the balloon equals the bottom pressure. That's why it's static. If you evacuate the balloon but keep it inflated, then there's no weight in the balloon, and so that imbalance is why the balloon rises. And so the same happens here. If this fluid happens to be denser than the water, then the pressure acting at this point in the red fluid will be larger than the pressure acting upwards by this. That's what the definition of this capillary pressure is. So this height of this fluid defines in some way the capillary pressure that's pushing this fluid to make it go into these smaller spaces here. So the capillary pressure will determine how big a height of this saturated lens can exist before it will actually invade and keep on going. And so that's really what we're attempting to determine. All right, so don't want to over-explain everything. So this is a generic capillary pressure versus saturation curve. This is what it looks like if it's dimensionless. This is what it looks like. Comes out of Baer's book. These happen to be for different, these would be petroleum reservoirs. Weber sandstone, Moreno, Viking sandstone, etc. So these all have different magnitudes of these capillary pressures, and if they're written in terms of this J function, they're not exactly equal to 0.3, which we had before, but they're not off it by very much. They're off it by a factor of perhaps 50% more, and maybe down to 1/3. So this span isn't very high. So this Leverett curve, which we've talked about here, this is our 0.3, which I drew. This is clearly a little bit fictitious in that this doesn't hold for every single material we have, but it holds reasonably well. So within the limits of this variability, this value of PC0 in terms of the Leverett function we can take as equal to 0.3. Okay. So, what else can we do with this? Well, we mentioned that the things that we'll talk about have been developed in a bunch of different fields. So some in petroleum, some in agronomy. So one way of looking at this capillary pressure versus saturation curve, if we just look at the drainage limb, so this is when water is draining out of the system, then we could characterize it in terms of this. I guess it's concave downwards, and then it's concave upwards in this case. It has this characteristic behavior. And it might be advantageous for us to define this by an expression which is easier for us to define. And so Brooks-Corey relationships are exactly that. So what we could do is we could take this graph, and instead of this we could divide this by the unit weight of the fluid. And instead of plotting this on a natural scale, we could plot it on a log scale. So we could take the log of this. And we could also take the saturation, and being from 0 to 1, we could also plot this maybe as a modified saturation, plot log of saturation. And if we did that, then this curve would start looking like this, with the proviso that we define the saturation in terms of an effective saturation. So the effective saturation is the saturation we find ourselves at. And so each one of these saturations would be these individual points on this curve. So this would be the saturation of water. So I guess it would be this. And if we subtract from that the irreducible saturation of water, then the length that we're talking about would be this length, right? So I guess I'm going to get too complicated here. This length here would be SW minus SW0. And if we take this length here, this length here would be 1 minus SW0. Right? This whole length here would be 1. If we subtract off this length here with SW0, it's this. So if we look at these two terms together and take these two together, look at the reciprocal of them, SW minus SW0 divided by 1 minus SW0, just these two terms. All we're doing is we're just cutting off this portion of the curve. We don't care about it. And so what we're doing is we're calculating our saturation in terms of this as a reference point instead of this as a reference point. Right? That's what this term is. And you'll see that's exactly this term here. So what we're doing is we're basically taking this curve and we're ignoring this part here. We're writing this as an effective saturation. And this effective saturation here goes from 0 to 1. That's what we're doing. So by doing this little jinx, we're just lopping off this portion of the curve and centering it on this. So it's useful to do that, because if we do that, then if we plot the effective saturation, this term here, and the capillary pressure divided by the unit weight of the fluid, and take the logs of each of these, and plot it on a different curve. So we've kind of switched it. This was saturation on the bottom now. Now it's saturation, effective saturation on the vertical. This was capillary pressure on the vertical. Now it's capillary pressure on the horizontal. But we can look at all of these ordinates. This bubbling pressure so called because a bubble of the non-wetting fluid enters first into the pore space. This is the first saturation of a non-wetting fluid getting into it. This bubbling pressure is this point here, which was here. This is also what we called PC0 on our curve. This term here, PC0. And now, if we plot it in log space, we take this curve, which has a kink in it, and it turns out to be just a straight line. Plots as a straight line. And so it's easy to define what a straight line is in log space. We can define it in terms of its gradient, which is lambda. So this is one log cycle, and this is how many log cycles are represented by that. It's just lambda. And it allows us to write the equation for this line as being this equation at the bottom of this page. I'll put them both on the same page at the same time. I can't do it. I'll write it up here. Log SE is equal to lambda, just writing this equation here. So the equation of that straight line is just this. The log of the effective saturation is given by the gradient of this curve, this straight line, not a curve anymore, multiplied by the capillary pressure divided by PC0. And this is PC0. And this is, this is any pressure on here is just PC, which is this, right? So this is just the equation of this curve. And so it's just a convenient way for us to be able to represent how the saturation changes as a function of capillary pressure. And so presumably, if we think that the capillary pressure is somehow related to the height of the fluid that's in the system, then we should be able to tell, for instance, how thick the lens or the puddle of the red fluids are in these systems. That's what we're going to want to use this for. So that's it. So that's the deal. So bottom line, this is what the curve looks like in terms of all its attributes: drainage and imbibition, entry pressure or capillary pressure equals 0, irreducible saturations of water and the non-wetting fluid. We can parameterize it non-dimensionally. It's useful for us to know that this number is equal to 0.3. And this kind of holds for all materials, but there is a spread in terms of these curves. It's not exact that they all fall directly onto these curves, but at least they're limited in their span by this Leverett function. And finally, we can take this curve and make it into a prescribed curve, which is a pretty simple relationship, which allows us to be able to do the calculations to calculate what saturations would be if we know what the capillary pressures are. And we can guess what the capillary pressures are if we know the heights of the fluids are in the system. So that's it. And so we've got that. And so perhaps spend the time. This is exactly what this is here. So this is exactly the transformation which we talked about applying before, that we're going from this curve in the field, and these would look like this if we plotted them in log space. And so we can think about the features of this and how they would turn up in this log space. So if we look at the highest bubbling pressures here, the one with the highest bubbling pressure is this one, which is number 4. And we'd expect this to be this one here, right? So that's no surprise. It's the furthest, has the highest bubbling pressure, so it's ordered here. The one with the lowest bubbling pressure would be number 1, which would be this one here. So that's exactly what these two would look like on this. And I guess the other feature of this is that the straight line here, the more vertical it is, then the more that as soon as you get to the bubbling pressure, it will invade the whole pore space in the system. So if these lines are close to the vertical, I suppose you'd expect that the porous medium would have all the pore spaces would be the same diameters, because as soon as it gets into the largest one, which it can get into, it'll invade the rest of the specimen. So the one here with the, which satisfies that, I guess, would be this one. This is number 2. And not surprisingly, number 2 is the one that has the flattest curve here. So in other words, once you invade this, this must mean that it gets into the biggest pore finds. Then it's looking for the next largest pore. You have to increase the pressure all the way up to here to get to this particular saturation here. So this would be a smaller pore, a smaller pore, and a smaller pore. But for number 2, as soon as you get entry here, it actually saturates the whole core, which means that all the individual pores are roughly the same size. So the steepness of this refers to the flatness of this, I suppose, in that particular space. But there's a physical meaning to this, and that means that as soon as you invade one pore, it gets into the whole sample. That's it. And so now what we're able to do is if we take the value from this, so I guess this would be, we said that the way to do this would be to measure 1 log cycle, and this would be the number of log cycles in the other direction. So if we do that here, it's not going to be very convenient for us to do it. I suppose the easiest one for us to do would be, let me do it with green. If I extend the flattest one here, here, and if I draw this to this, then this is 1 log cycle here, right? Going from, this is in centimeters of water, so this is the length. Capillary pressure divided by unit weight, newtons per meter squared divided by newtons per meter cubed as meters or centimeters. So this is going 1 log cycle, and so this lambda would be equal to 1, 2, and 2.3, right? Is this 0.3 of a cycle? This is 1, and this would be 1, obviously. So that's how you measure it. So you're measuring them off in log cycles. And so that gives us your equation. So just to remind you, log of effective saturation is equal to minus lambda log capillary pressure divided by PC0, or bubbling pressure, whichever it is. So it's just a convenient way to be able to represent that expression. Okay? So what else? So the other observation is, maybe going to this, is that these curves, if we look at realistic curves, so it's a bit like what we had before. So if we draw, in terms of our terminology, this is the bubbling pressure, or PC0. This is the irreducible saturation of water. This would be the irreducible saturation of the non-wetting fluid. We defined those terms before. And so these areas here, this irreducible saturation is kind of no man's land. You can't get into this location. So this means that as you push more non-wetting fluid, more red gasoline into the porous medium, it pushes the water out. But at some stage, you can't get any more water out because there's this monolayer of water coating the grains, and you'll have it present as this pendular saturation, I guess. These rings that are around the contacting grains. So that's what this would look like. So right here, I suppose would look like grain. Oops. And so this would be right. So this is water that's left here in red. I shouldn't be using red because we were using it the other way around before. And everything that's filling the pore space is the non-wetting fluid. And so this is what it would look like here. Then as you come back down here on the imbibition curve, it sucks in water naturally as you reduce the pressure in the non-wetting fluid. And I guess if I would copy that. Oh, fantastic. And this would look like something like this. This would be much more water, and by definition, these are two grains. Of course, there's grains next to it. If the water is filling up the pore space, then there's no room for the wetting fluid. And so as it comes down, it would start filling up with water. I guess the point I was making on this diagram is twofold. One, that these zones here are zones in which we really can't get to it. So we're left with this amount of water always within the system. So it might be 20, it's not a trivial amount, it's 25% in this case. And then, as Sean noted out, as you come back down here, you don't go back to 100%, you're left with a smear of the non-wetting fluid present within the system. And so at this point here, I suppose in the figures that we used before, if we get to them, this would be the bubble of the non-wetting fluid in the middle. This would be water all around it, so-called funicular saturation. It sits in the middle as a bubble, whereas the water, when it's at irreducible saturation, is this little donut shape around the individual contacting grains, and the rest of the non-wetting fluid is filling the pore space. And as you come down in capillary pressure to this funicular saturation, then this is the lowest, this is the most amount of the non-wetting fluid that you can get out of it, and the non-wetting fluid will sit as a bubble inside the water saturated part. And this represents the behavior that you have at this point here, right here. And so we need to understand a little bit about these irreducible saturations. That's what they physically mean. And I guess the other point on this figure is that there's hysteresis in this. So if you keep on pushing the non-wetting fluid in by increasing the pressure to get to this point here, and then you stop increasing the pressure and back it down, it doesn't go back down this curve here, but instead it goes across in these so-called scanning curves. And so it goes down here, and it would ultimately end up down here. If once you get here, you stop, or you go down to here, and then you increase the pressure again to push more wetting fluid in, then you go up another scanning curve. So these are, you can imagine a whole series of these crossover curves that represent here, depending on when you raise and lower the pressure. And so the reason for this is that simplest explanation is that the interfacial tension of a surface and the angle at which it joins depends on its history of wetting. If it's been wet before, this surface has been pre-wet and it's receding, the contact angle here is less, And this is a portion of the windshield that's newly going to be wetted by this raindrop running down the windshield, and so the contact here is much steeper. And so the fact that it remembers whether it's been previously wetted or not, and this means that its behavior, in its wetting behavior on the grains, crosses over on these scanning behaviors. So it's really quite a complicated system. We try to describe it in terms of capillaries, single capillaries. Perhaps those are useful to understand the fact that we have hysteretic behavior, because you could imagine seeing a raindrop running down a windshield, and it matters whether it's been previously wet or newly wet, and it explains these processes. I'm probably going to leave it there. It's probably enough drinking out of the fire hose for today. The point of this is that if you think about the capillary pressure versus saturation curve that we've just drawn, we could imagine using that. So now we know what this bubbling pressure is, in theory. We know that the form of this saturation changes as you change the capillary pressure within the porous medium. But we could think of that kind of as being the column of the fluids that are present in the subsurface. And so we made no distinction of the fluids other than that they're wetting and non-wetting. We're kind of thinking of them as two liquids, but that's perhaps, we could also think of them as water and a non-wetting air. And if we did that, that would represent the behavior in the vadose zone. So this means that the tension saturated zone is that the aquifer is fully saturated above the water table. Water table by definition is where the pressure at the water table is atmospheric. But as you go above that pressure, the actual water pressure is in tension, so it's less than atmospheric. And so this is being held in place by the tension in the water. Once the pore spaces get large enough, it can't sustain that high column of water, and then it gets saturated with air. And so this amount here would be, if I draw it here, would be the saturation of air, which is the non-wetting fluid, and this would be the saturation of water as you move up here. And the point only to make, ready for next time, for which you'll be on your own, you might be happy to know, is that these curves that we've spent so much time laboring over and trying to understand allow us to say exactly what the saturation would be in the column as we go up in the porous medium. And of course, it would also allow us to say what the saturation would be as we go down below the surface in looking at the saturation of the portions that make up the lens of fluid which is in present. So what we're trying to do is, if we go back to here, is we're trying to have a rational way of saying exactly what the saturations would be in this portion here, what the saturations would be here, right? We already know from what we said today that it's probably not 100% saturated with the red fluid. It's going to have irreducible water in there, so it might be 20% water and 80% NAPL. Here we'd expect this maybe to be 80% water and 20% NAPL in this sphere, in this smear. And we can rationalize exactly what those distributions should be by using, I didn't want to do that, by using this kind of process. And so we don't need to do that here, but notice for now that this is a capillary pressure versus saturation curve, which we're overlaying starting at the water table where the capillary pressure is 0 and going upwards. And we're starting at the water table with a DNAPL going down below the water table, flipping the diagram upside down to be able to say something as to how the saturation of the non-wetting fluid, which will be, this would be the saturation of the non-wetting fluid, and this would be the saturation of water as you go down. And what it's saying is that as you get a higher column of the non-wetting fluid above you, you'd expect that the saturation of the non-wetting fluid would be more and more as you go down. And of course, in the limit, it will be a puddle, which is nearly 100% saturated, but with irreducible water still present within it. So we're not doing it for no reason. I guess you can all see why we do that. And I guess the other ulterior motive we have on doing that is that if we now know what the distributions of fluids are within this column and within this lens, we also know how much mass we have to be able to remove if we're going to remediate the site. And so we can say something quantitatively about how much stuff we might have in place. So that's what we'll talk about. That's what you'll talk about next time.